time shifting later. So whether you're watching this live or whether you're watching it later on demand, we want to welcome you. It is 3 p.m. here in the Eastern time zone, and I want to get started. But whatever time it is for you, whether live right now or later on, welcome. I'm pleased to welcome you to the fourth webinar in our fourth CapTech Talks Plugged In series having to do with robotics. These plugged in webinars are specifically designed for high school and community college students, but are actually open and available to anyone interested in the topics. And we have many times have had faculty, current students, former students, as well as guests join us for these sessions. This is, as said, the fourth in the series of the Robotics Certificate series, but actually the sixth in our series of plugged-in talks for the fall. We've been having these almost every week since September, and we'll have two more following, one more on November 6th and the last one on November 13th. I will talk a little bit more about those last two sessions in a little bit. This session is session 4 in the robotic programming series and, the robot certificate series. And this one is programming and visualization. And it's going to be presented primarily by Dr. Ruhul Tikekar and Zach Liebowitz, assisted by the coordinator for the entire 4 sessions, Dr. Vijay Kotha. Now, let's talk just a little bit about the agenda that we'll be following today. It says Cameron Newsom is your plugged-in host. I am actually sitting in for Cam, and my name is Bill Gibbs. I'm on the graduate admissions staff and handle all the webinar coordination. We'll talk a little bit about Capital Technology University and then a few session pointers. Then Dr. Kotha will introduce the robotics series to us and our presenters. We'll have the presentation Q&A time following the presentation, although I'd like to mention that because of the informality of these sessions, if you have a question, pose it at any time. You can pose it either during the presentation, either in the text chat box or the question and answer box. The text chat box, everybody will see. The question and answer one, only you will see your question, but all of the hosts and panelists will see it. And then we'll talk finally about the following webinars coming up, and then also how to get a copy of the recording and a certificate. We'll cover that in more detail later. I have just 3 slides about Capital. I don't want to spend a great deal of time talking about the university, as many of you are very familiar with it. But in case you're not, we are a nonprofit, private accredited university based in Laurel, Maryland. Our physical campus is in Laurel, Maryland, although we have a large audience of around the world of students studying in many different countries. We are fully accredited by the Middle States Commission on Higher Education, regional accreditation, which is the highest level of accreditation available in the United States. And we're also authorized by the state of Maryland, where we're located, to confer everything from associate's degree to bachelor's, master's, and both PhD and Doctor of Science degrees. We are an award-winning and STEM-focused university. We won earlier this year the very prestigious SC Media Award for the best cybersecurity higher education program in the United States. We're the only independent college in Maryland dedicated to engineering, computer science, information technology, and business. We're STEM-focused and award-winning. And finally, I just want to mention very quickly a unique guarantee that we offer to our undergraduate students. Our guarantee is that if you graduate from Capital Technology University with a bachelor's degree, you will find a position in your field within 90 days of graduation. And if not, we'll offer to you up to 36 additional credits tuition free so that you can continue your studies and your job search. But we don't often have to do that. Even in these times, we have had great success in placing our students within 90 days of graduation. The fields that our students graduate in are ones that are in high demand, have been for many years, and will continue to do no matter what is happening economically in the United States or around the world. We can do this because our return on investment is so good. Recently, a study done by Georgetown University showed that we're in the top 3%, actually 2.6% of all 4,500 colleges and universities in the United States for the lifetime return on investment your money invested into our college education will give you. A tremendous accomplishment, one that spans almost 90 years of working with students in the STEM fields. Session pointers. We're done with the commercial for the Capital Technology University, and we'll go on now to the session pointers. We'll answer questions at the end of the presentation, but anytime you can post a question, and it'll be up to the presenter as to whether he'd like to answer that question at that time or hold it till the end. We're not authorizing or equipping microphones and webcams for participants today. So anytime you want to communicate with us, do it through the text chat or the question and answer box. We'll make sure that you get a link to the recording, and that will be sent to all registrants, whether you're attending the live session or on demand. And we will make sure that you have as well a copy of the slides. And if you wish to get a certificate of attendance or a participation for the 4 series webinars, then you can do that. The session should last just about 60 minutes. Now with that, I'd like to have our coordinator for the robotics series, Dr. Vijay Kotha, to come on board and introduce the series and our presenters for today. So go ahead. Let me make sure that you are unmuted and have video.
I think I'm on video, but you guys can tell me. Hi, I'm Vijay. I'm so glad that you have been with us for the last 3 events. One on the history with Leslie, one on the design with Steve, and on systems engineering and sensors with Raj. Today is the 4th session on programming, and the best people in town, Rahul and Zach, will take you on our mission to get you into the Raspberry Pi mode, to get you to think about programming, because that's the money where you will have careers that you would want. And we, as mentors, as we have been in Prince George's County for 20 years, helping kids go from middle school to graduate school. And our job is to be there, smile, work with all of you. So as you will be hearing from Rahul and Zach, the key is perseverance. You need to put in the hours, and we are there to help you. Again, we have events coming up, a Saturday tomorrow for Halloween. We expect you to come as from Capital and high school to show your pride of what you like to do. And when you come over to our makerspace tomorrow, you get to see the PiMars challenge with the 12 by 12 arena. The best part is all the 4 robots function, and you understand the depth of the problem, how multiple robots working together can enable a solution when you work together as a team. But right now you have an amazing presenter, Rahul, who has been mentoring our girls at the Blade Runners team with Jamie Price. Jamie was our mechanical designer mentor, and Rahul was there to help. Again, Rahul learned as much from the girls as the girls learned from him. And the same thing allows that when Rahul was there with Jamie for the 3-day robot build at Capital College, Zach was there to enable technologies. And with that, with the team mentoring, the kids built it, and it was fun to see the sausage being built. So what you have heard of the PiMars is an idea that has come to a reality. So we have multiple PiMars in our space, and you're welcome to use them. You are welcome to learn with them and welcome to grow with them. And if you continue with us after this session, on the 7th, we are building up kits. We're going to be sending out to Bahamas, and you will be our ambassadors. Not Rahul, not VJ, not Zach or Jamie. It's you, because you have been the wherewithals that you can take why all these are important. So the glue that holds everything together is programming. And Rahul did his graduate school after coming from India in Bangalore, in Dayton, and after PhD in computer engineering, he went over to teach in multiple universities, and then decided that he wanted to be in a government career in research, and he's at the IRS right now. And Zach is a colleague of mine, who used to be a colleague of mine at the Electronic Warfare Division at NRL, and you'll be hearing about Zach at the end. So I'm going to give the podium over to Rahul, who will be taking over the reason why you need to code and what the benefits are. Over to you, Rahul.
All right, thank you. And yes, let's move ahead and we'll start the presentation right now. So Rahul and Zach, I give it to you.
Okay. Good afternoon, everybody, and I hope you find this session useful and inspiring. I'm going to speak for a little while, and Zach is going to do a demo for you. That's the agenda. And you've been following this robot last 3 weeks, and today I'm going to take one aspect of that particular series, which focuses on programming. So let's start with, let me see if I can get the slides to move forward here. Hang on. There we go. So, here are some questions to ponder. Assuming you find yourself on an airplane to be the only passenger, somehow all the others vanished. Question is, how can one land the plane? The plane will land without your help, but how? Take a modern car, and for example, I'm going to take Mazda CX-5 here. How do you optimize the movements of the pistons in the engine to maximize gas mileage? You know, there's a big push on trying to get as much out of 1 gallon of gas as possible. So in order for you to do that, the combination of the spark, the oxygen, and the fuel that creates the explosion in an internal combustion engine and moves the pistons. So how can you optimize them so that you get the best gas mileage? Now, I don't know about you, but I like to watch football on TV on Sundays and Mondays and Thursdays and Saturdays. And when you watch football on TV, you will notice that they draw these 2 lines for you. One where the ball currently exists, and then how much more you need to go to get to the first down position. So you see those 2 lines. You know, those lines are not actually on the field. They are drawn on your TV. How do you draw those lines? How is a car like Tesla able to drive itself? If you have a modern car that was made in the last 2-3 years, you know you've got lane centering, dynamic cruise control, automatic braking when something comes happen. How is all of this possible? And the answer is, if I can move, there we go. Software. Software is what I was looking for. So if you got software, yeah, you're a winner. So software is nothing but a set of programs. It could be a complex piece of software, and it'd be complex computer programs. And these programs run on computers and make things happen. So an autopilot on an airplane is a piece of software that flies the airplane, and it can also land an airplane. Face detection on your phone's camera when you're trying to take a picture, and you can see a little square or a rectangle that crops up on faces. So your phone, the computer in your phone, is able to recognize a face in a picture. If you have used Gmail, as you're typing your mail, Gmail recommends words. It tries to complete your sentences. So all of this is possible because of software. So the objective of this talk, and I'm going to try and see if I can speak very fast so I can get to the part where Zach can show you a demo, is to understand what's programming, how are programs written, is programming difficult, what knowledge is needed to be a good programmer. Of course, what does all of this have to do with robots? Because this series is about robots. And then if you are going to CapTech or are interested in going to CapTech, you want to be an engineer and build things. Do you really need to know programming? And I hope I can get through these questions in the next few minutes. So to begin, it all starts off with the concept of an algorithm. Take that word and write it down, because that is probably the most important aspect of all of this. An algorithm is a set of well-defined instructions to solve a computational problem. Typically, we don't use the word algorithm for your daily life. So, for example, a recipe to bake a cake. Those are well-defined instructions, but you're not using a computer to solve that. So, an algorithm, we try to limit it to a computational problem, problems that can be solved on a computer. It's written in an English-like language, and that forms the basis for all software. Of course, before you can start on an algorithm, the first and the most important thing is that you make sure you understand the problem. Otherwise, you cannot solve it. Once you've understood the problem, think in your mind, how can I solve this problem with a series of sequential steps? So here is an example. A very, very simple example, almost trivial. You want to add two numbers that a user is going to enter from their keyboard. So you've got those sequence of steps. The first step would be to print, hey, enter a number. And then you read a number. Then you say, okay, enter a second number. You read the second number. You add them together and put them in a container called sum, and then print. So as you can see, this is an English-like language. It's also called pseudocode because it's not really programming. It has elements of a programming language in it, but not quite. Now, this is a language that I came up with. It's not necessary that all algorithms be written in this way. The idea is to be able to write something down which is not tied to anything. This helps a reader understand the nuance, the actual objective, the sequence of how you do something. So once you've got that algorithm down, we can move on to other things. Here's another example of an algorithm. Again, a fairly trivial one where you want to find the maximum of three numbers that the user is going to enter. So you're going to read number 1, number 2, number 3, and then max is what's going to be the maximum. And you assign the first number to be the maximum for now. And then you look at the other two numbers, and if number 2 is greater than max, then obviously max becomes number 2. Then you look at the third number. If number 3 is greater than max, then max becomes the number 3. Otherwise, nothing changes. And you print the largest number. So that's an algorithm. The second stage of a programming adventure is to take that algorithm and convert it into a program. A program is the algorithm in a particular language. You've got to choose a language. There are so many. These are the popular languages that are in use today. Java, Python, currently the most popular one, C, C++, Julia, the one that I like, Go, C#, Rust, Scala, JavaScript. Each language has its syntax. Algorithm does not have a syntax. You write it in the way you like it, in a sort of a pseudocodish way. But once you start writing it in a programming language, you've got to follow its rules, its syntax, and its quirks. So here is an example of taking that program that, or the algorithm that we wrote to read two numbers and sum them in Java. So Java has its way of writing things syntactically. So that's how it looks. Now here is the same algorithm, but this time written in Python. Moving on. So the first question that most people want to ask is programming hard? It's a relative question, but in general, no. All you need is a logical and methodical way of thinking, and most of us always and already do that. The idea is to take a problem and then break it into smaller logical units. Then take each unit and then further break it down into smaller logical units. And then again go down to that unit, each unit, and break it down. So you keep doing that until the instructions in each unit are sufficiently simple or basic. Now, one of the things I recommend and I try to emphasize in a programming class is that knowledge of math is very useful, because most of the time what you will be doing is solving a problem that relies on math. So you're taking the problem, mathematics provides the solution, the algorithm writes it down in a computational manner, and a programming language actually goes into the computer. So programming's greatest challenge then, just the programming aspect, is to understand or learn the syntax of a language. And that becomes easier with each program that you write until it becomes second nature. So the programming is really not the complicated part. It's the development of the algorithm. Of course, how is all this related to robots? Well, without software, a robot, as you can imagine, is going to be a fairly expensive or a fancy paperweight. It is software that's going to make your robot achieve its purpose in life, whether it is to sort balls of different colors, be it to shoot a basketball into a hoop, or be it to go and find and defuse a bomb. So, for those of you who may be keeping track, NASA sent a robot, and it's called the Mars rover, to Mars. And that is an excellent example for all of you engineers to be, of an example of a robot on a mission. So this represents a combination of engineering excellence, because you've got to build this robot to go into a completely different environment. And then software needed to make that robot do something so we can study the planet of Mars. So a robot would typically consist of three things, broadly speaking. A computer or a control unit. Like it could be a Raspberry Pi, it could be a RoboRio, it could be an Arduino board. Then you're going to have sensors, like a camera. In the last lecture you saw a ultrasonic distance sensor, LiDAR, a gyroscope, IMU, various sensors that kind of tell you what's going on. It's akin to a human body. We have sensors, our eyes, ears, nose, hands, touch. And then actuators. Actuators are things like wheels and pulleys, arm, etc. So typically a robot consists of these three things. So then when you take that robot, the programming aspects are based on three pillars. Sensory, as I said, what is around me? Could be a stop sign, a curve in the road, a red ball. An actuator, what should I do? Do I turn? Do I stop? Do I pick up? Do I go up, go down? And the control, the brain or the decision-making system. So a useful robot would go through a continuous loop, read sensory information, trying to understand where you are, what you're doing, do the necessary computation, how far is the stop sign, should I turn left, is there somebody in front of me, decide on the best course of action, it's the algorithm, and then send instructions to actuators to perform those actions. So here's a quick example. How much time do I have? Okay, I have about 5 minutes, so we're good. So here's an example of a problem that you saw being solved in the previous presentation by Raj. We are trying to determine a distance. So you're trying to program a robot, and your job is to figure out how far you are from maybe an obstacle of some kind. And so for that, you need a sensor. And we use this ultrasonic sensor, which works on the concept of emitting sound waves. So as you can see, there are two round objects there. So you emit a sound wave. The sound wave goes and hits an obstruction or an object in front of you. And as a result of hitting it, there's an echo. So it comes right back. So the second object there captures that. And then you measure the time it took for the sound wave to go hit the object and come back. So now you're going to try and formulate an algorithm. But first you need the math. Remember, I said you need the math to do something. And what is the math here? The math is you're trying to compute the distance. And how are you going to compute the distance? Well, you're going to measure how long it took for a sound wave to go hit an obstruction and come back. So for that, you need to know how fast sound travels. So a simple calculation there tells you, you take the time taken, multiply it by the speed of sound, and if you divide that by 2, it tells you how far the obstruction is. The speed of sound is 343 meters per second, or 34,300 centimeters per second. So armed with this knowledge, we're ready to write our algorithm. So let's put this in. So if you look at that sensor, it has 2 pins. One is the trigger pin that emits the sound wave, and one is the echo pin that listens to the echo. So when you start off, you want both to be low or 0. When you're ready, you go ahead, emit the wave. So you raise that trig pin, the trigger pin, to 1. In other words, give it a high voltage. Then you wait for a second or so it kind of settles things down. So you've sent the wave. Now go back and reset that trigger pin to 0. Now our job is to wait and listen to the echo. So now the echo is going to come back to you on the echo pin. So if the echo pin is 0, you just have to keep waiting as the echo back, is the echo back, is the echo back. So it's in a loop. You're going to wait until the echo goes to 1. That means, yep, I got my echo back. So as long as it's not coming back, I keep measuring the time. Okay, until it comes back, I'm going to keep checking what time is it, and then once it comes back, I know what time it was. So I have these 2 times. Now the time taken for that sound wave to go and come back is the difference between the time when you sent the wave and the time when you received it, so the actual time on a watch, stopwatch. So once you have the time taken, we use our formula for math, which says distance is time taken times the speed divided by 2, and there's your distance. So that's an algorithm, and that's written in an English-like language. Now when it comes time to code it, it would depend on what language you want to use. So if you wanted to use Python, that algorithm would look something like that. So we have a certain challenge in robotics, and Vijay was talking about this. Let's say you've got multiple robots designed by different people in a room. So one might have a Raspberry Pi, one might have an Intel-based computer, one might have a RoboRio, another might have an NVIDIA Jetson. These are all different robots with different operating systems and different hardware. How do you manage them all together? How can you communicate with them and make them achieve a common objective? One possibility is each one talks to each one all the time to decide where they are, what are they doing, what should they do. Now, that's difficult to implement, and it doesn't scale. As the number of robots increases, that becomes just too much, and it's error prone. So the answer to that is something called ROS, or the Robot Operating System. The Robot Operating System is a set of tools. So it's a set of software, multiple software put together and packaged into one entity called the Robot Operating System. So what you do is you take that software, Robot Operating System, and place it on each robot. And now you've got a common way of communicating with each other and implementing functions. So ROS doesn't just let you communicate, but it also lets you do things. So it's something that you might want to consider, and I can't go too many into detail about ROS today because I have so little time. But I want to impress upon you the usefulness of tools or software that make certain things possible. So to conclude, software is ubiquitous. It's everywhere. It makes our lives more interesting. Software is a result of writing programs. But most importantly, software is laid over the foundation of mathematics. So an engineer who has an expertise in programming is a highly desirable individual, and you won't need to wait 90 days to find a job. It'll be like before you even finish your degree. So my suggestion is, if you want to do engineering, that's great, but I would recommend that you either get a minor in computer science or mathematics. That would be an ideal mixture. And I recommend this highly to people. Many years ago, DARPA designed a challenge: design self-driving cars. And universities competed to win this grand prize. So if you go to YouTube and watch that, this is the early stages of self-driving cars. We're talking about 10 years ago. And you will notice how engineers and computer scientists come together to work on a project. It's an excellent watch. So I'm going to hand this over to Zach now, who's going to show you one aspect of programming for robots, and that is computer vision. How do you look at an object and decide if it's a blue ball or a green ball, or if it's a square or a sphere, and things like that? So he's going to take you through a demonstration of a particular type of software called GRIP. And Zach, off to you.
Okay, I'm going to stop my screen share so that we can have Zach take over here. There we go.
Okay, so I'm Zach. I'll be talking today about computer vision, briefly at least. So computer vision is kind of interesting nowadays. There's kind of two classes of techniques. You have classical techniques, and you have more modern techniques. The more modern techniques are primarily based on neural networks, which is an entire area of study. I think I will skip that for today, although I'll come back. I happen to run ahead of schedule. However, what's interesting with them is if you give them a lot of data, they will learn well, and they'll do better than the classical techniques. However, you have the requirement of a lot of data. You need time to train it. And if for instance, you're designing a robot to run in a relatively dark room, and you train it in a relatively dark room, and suddenly your world turns bright, it might be a little bit hard to adjust it, and you might need a lot of new training data. Not as much as originally, but you'll still need to adjust for that. And the classical techniques are kind of nice in that they're a lot easier to understand and a lot easier to manipulate. A neural network, you can't just go in and say, okay, I want to change these 5 values, and this makes them work better in bright rooms. You just don't have that insight into how the model works. And most likely, that information is just kind of encoded in large part throughout the entire model. So that's kind of these techniques, modern techniques in a quick view. And neural networks are used all over. AlphaGo and modern speech recognition systems like Siri or Google Assistant use that same technology, and it's extremely effective, as I said. However, there are certain problems, and a lot of them are kind of in the category of if you can express them well with these classical techniques, you're better off doing so. If you cannot express them with the classical techniques, you're better off going for the more modern techniques. So GRIP here, which I have the homepage here for, you can find it by Googling GitHub FRC. GRIP is a tool for doing more conventional computer vision. And as far as FRC, that's First Robotics Competition. First Inspires is a national nonprofit, or actually international nonprofit, that has a number of robotics competitions. They're great for anyone in K through 12. and Vijay had mentioned those briefly with regards to some activities that the various speakers have worked with. And yeah, highly recommend it. If you know people who might be interested, you should point in robotics, point them to it. If you're in the local area and their schools don't provide it, Vijay is a great contact person to find local teams that are able to take in extra people. But anyway, let's go and move to the tool. So the first competition has a number of different, I'll call them props that are used as part of the thing. In this case, it's what's called a boiler. I believe up above this thing is some holes you're supposed to try to shoot some balls into, where the balls, I believe, are fuel. Anyway, the details aren't terribly important. But what is important is that you want to find the spoiler. You might be a little bit away from it. You might have weird angles to it. And in certain cases, you could be farther and farther away. And you want to kind of be able to handle all these cases. And you notice here how many different images we have. This is actually a set of 33 images. And we're going to start off with this image up close just to kind of calibrate with. And you want to find the boiler. The most easiest feature kind of when you're looking for this thing is this blue colored stripes. You'll notice that there's a bit of difference in the lighting here. You can kind of see where the sun's hitting, or not the sun, but the lighting system's hitting it, however that might be. So what we're going to try to do here is just take a simple threshold. Basically, we're going to set colors in computers are represented as RGB, red, green, blue, which is kind of the computer equivalent of primary colors. And we're going to try to just go ahead and segment according to that. So what I'm going to do is I'm going to hook up this image to this threshold, and I'm going to go ahead and pop up an image here. You don't really see anything there yet. What I'm going to do is I'm going to say you have to be at least a certain amount of blue, and you see this region starting to turn black. The black here is parts of this region that we're rejecting, that we're saying does not meet our thresholds. And just to make this a little easier to work with, I'm going to add this mask in here. What this mask is going to do is just take this image here that can be thought of as basically on or off. If you're this whitish grayish color, I'm not entirely sure how it's displaying on your screens, it's going to be on, and if it's black, it's off. So we hook up the mask here, we hook up the original image here, if I could actually drag. And then I can go ahead and display this picture here where you see the black laid out on top of the original image. And let's go ahead and continue working this. And generally with these type of things, you create these kind of pipelines where you do multiple steps. And generally what you want to do is you want to over select things. So we kind of keep just moving this until we start removing a bit of our blue. And I think we're good about here. Because it's blue, we don't really want to change the high side of it. We're going to try to reduce the amount of green that we're seeing here, and we really can't do much. We try to reduce here as well. I'm a little bit nervous on this part, but we will give that a shot. And we're going to try to reduce the reds as well. And we seem to be doing a pretty good job here. We're seeing little bits of regions here that are blue that aren't actually matching our stuff. We can try to handle that in a later post-processing step. But you can see we're doing a pretty good job here. So at this point, we'll go ahead and flip through some more of our images. So we're doing all right here. We're doing, well, here we kind of get all this area, which isn't great. And I really hope you can see my mouse, I guess, but just in case you can't, it's kind of the left 1/3 of the image where you're seeing the stuff behind the cage there. So we're kind of selecting the blue. We're still selecting a little bit too much here. And at this point, what I want to do is go ahead and kind of change the problem a little bit, which is not an unusual technique in mathematics and programming, which is I want to change the representation of the problem to something that's a little bit simpler to work with. So RGB, it can kind of be represented as these cubes here. And what you'll notice is, well, okay, first of all, let me explain the cube actually. This bottom right corner of the cube is the blue corner. the top back right is the green corner, the bottom left red is, or bottom left is the red, and this top front is white, and basically the bottom, well, the corner that you can't see is black. And basically, you kind of see here that the colors don't really blend that well. You have these very strong blue regions, these very strong red regions, and then you have these smaller regions where colors kind of mix. And that's not a great thing from a color selection perspective. There's two alternative representations that are commonly used, HSV and HSL. I'm going to arbitrarily choose HSV here, although HSL is also great. And basically, you can see here that the colors are changing much more smoothly. The HSV is the two images on the right, and these are just kind of cross sections. Rather than being a cube, they're spherical, and you can see that you have roughly equal portions of different colors, and that they're very smooth. It's not like you can't really describe like a hard boundary like you can with this RGB cube. And there's an entire amount of color theory kind of goes into that. So what we're going to try to do here is rerun the same process we just did and do this with HSV in order to see if we can get some better results that generalize a little bit more. And I should add, this is a very typical problem to run into where results don't generalize very well. And this is kind of where these pipelines become very useful in that you can kind of work on steps. You take a first step where you try to not filter out too much, and then you take another step that tries to do things a little bit differently, and you kind of keep adding these steps, and they combine to provide something that's very reasonable to work with. Okay, so the first thing you notice here is the blue is kind of bright. The value is roughly lighting amount. You can see with just the value here, we've actually removed a lot of the space. There's some stuff in around this middle here that we kind of want to remove. So we'll continue trying to do that. And we're doing a pretty good result here. At this point, we're only extra thing we're seeing is this right here. And the color filter's not really going to help us there. So we'll go ahead and check our other images and see how well we're doing here. And unfortunately, we're having a similar issue here, but let's see what we can do. So if we move this, we're getting into our blue. Let's see if we can continue doing a little bit further here. And we're actually removing this from the color spectrum. You kind of see here how this all works. And a question that I probably should address here is this isn't really programming, and that's true, but this tool can actually produce code for programming, and this is a very thin wrapper over a library called OpenCV, which provides all sorts of functions for computer vision, CV being computer vision in this case. And yeah, I encourage you to take a look at this tool if this at all seems interesting. It can do videos. You can have it read. You can import a video in. You can read off your webcam, and it's a kind of a great way to experiment with some of these more classical techniques. And if you go to the web page here for GRIP, there are some links to tutorials that will give you some more detail on creating these full pipelines rather than just this first step of a pipeline that I've shown you. So at this point, unfortunately, I can't really see questions about screen sharing, so I'm going to go ahead and turn back over to Ruhul for sharing a screen and for answering questions, or beginning to answer questions for either him or myself.
Okay, thank you, Zach. I appreciate that. Let me see if I can get my screen share set up again, and so that we can go on from there. And I think then, Vijay, before we go on, since the next slide, before we take any questions, the next slide has to do with the Schramm Fest. And if you can go ahead and talk about that just a little bit. You mentioned it earlier on, but the slide is right here, and then we'll go on to the questions from there. Okay, he may not have audio. All right, let me just read what you have, what has here, and then if he does come on, we can go ahead and answer that. He invited you to this event that is
I got it.
perfect, perfect, good, because I don't know anything about it, and I'm in Texas, so I'm not going to be very helpful to you. Go ahead, please.
So essentially, we have the four-wheeler robot based on Raspberry Pi. So we have made it available for students to come, learn to code. Rahul, Raj, and all of our mentors will be here. And the key here is you're going to have fun and see the arena, the 12 by 12 arena, the PiMars arena, and test out your ideas on how do you locate the lost Mars lander. So the idea is to have fun. And when you are here, you can also do other things like learn to do a little bit of electronics, fly quadcopters, and we have hopefully a model train that also runs on Raspberry Pi. Again, these are the ideas that we will be showcasing tomorrow at the Makerspace, and it's open and available for students. And finally, after that, there's a science cafe talk on hammerhead sharks and the biomechanics of it. And you can come virtually if you don't want to come to the Makerspace on the Zoom link at the Greenbelt Rotary website. So once you come in at 12:45, you get to hear a talk. And then at 1:30, we all move from our Makerspace a mile north to Shrom Hill Park, where we have festivities set up for students to do drones. We have students driving the robots and being in the open space where you can dress up in your favorite Halloween costume from your schools and meet and greet fellow Rotarians. And again, you will be in this bigger network of mentors who want you to succeed. So the idea is Capital College has a start of a Rotary Club, which is called a Rotaract. And we are starting high school robotics interact clubs with Rotary. So the idea is that we will be providing these software tools on systems that we will be giving away to other countries. So on the 7th of November, after the Shrom Fest, we will be fixing 150 laptops that will be dual booted with Windows and Linux. So I'm looking forward to all of this, but key here is join us if you can virtually or come physically and have fun.
Oh, perfect. Thank you. Okay. And I want to make sure that I understand correctly that, for example, for myself, who I'm 1,000 miles away from where the park is, that I should join virtually by going to the Rotary Club of Greenbelt. That is greenbeltrotary.org, and that's where I would log in for the Zoom event.
For the Capital, for like the Capital Zoom, we have our own Zoom link that we can come and listen to the lectures.
And that will be at 12:30 Eastern time.
That's correct.
Okay, good.
But the coding starts at 10 o'clock. That's physical.
Okay. All right. Good. All right. I'll make sure that this recording gets out to all of our on-demand guests this afternoon so that they're well aware of this. We talked a little bit about it last week, but I want to make sure that we did not have this slide available. Now, with that, we are going to go on to the next slide, which is the question slide. And I don't see any questions now, but I'd like to, anybody who's attending this live session, I'd like to open the floor either up to Rahul or to Zach for any questions that you might have. And I'd like to start with a question, not having a programming background or a computer science background myself. And if I wanted to go to the web and just do some fun projects just to start getting into coding and programming, what would you recommend? That's my first question, and we'll look forward to see if there's any other questions that have come in from the attendees.
Let's say that is as good a question as it is difficult to answer.
Sorry about that. I didn't mean to throw you a hardball right away there.
No, the reason it's difficult to answer is twofold. One, of course, as I said, My recommendation is always to start with understanding algorithms and developing algorithms first, and then moving on to a programming language. The second issue is, of course, choosing a programming language. Now, if you haven't done programming at all, then Python is a good language to begin. And if you go to python.org, they have a wealth of resources that helps you get started with Python, and I believe they also have an interactive session there where you can write programs for problems that they recommend. So that might be a good place to start.
All right, excellent, good. Let me check and see if there's any questions that have come in here. I do not see any. Just throw this out to the attendees. Do you have any questions you'd like to do? Again, either text chat them or put them in the question and answer. We'll give you a moment to do that. All right, I do not see any questions popping at this time. If others are like me, they probably think of many questions as soon as we log off. But I'd like to say that we're doing great on the time. Let me go ahead. I'm going to go ahead with my section, and then I'm going to return one more time to Rahul and to Zach and to VJ if there's any questions that pop while I'm talking. So I'll go ahead and continue on at this point just to cover a few things that we have left over in the webinar. Now, next week, I'm really excited about. We will have completed our robot programming Mars robot sessions, our 4 sessions, if I can just spit that out, and we're going to switch gears completely and go into physics and talk about that perennial question. I am not only a parent but a grandparent, and I've already been asked by my grandchildren why the sky is blue. I'm eager to attend that session next week so that I can give them a good science-based answer and not just say because Grandpa says it's blue, that's why. Now, on November 13th, we'll have the future of unmanned autonomous systems, and our presenter today talked a little bit about the programming behind a self-driving car, but there's far more than cars. There's, of course, aerial vehicles, aerospace vehicles, satellites, and as we already mentioned, a robot that has been on Mars. And so this, we're going to have one of our recent graduates who is an expert in this area talking about that. To join any of those, just simply to go to the captechu.edu/webinar series. These are not the only webinars that we're offering, and I'm going to talk a little bit about another set that is coming up here as well in a moment. I will be sending a link to all of our registrants. We have dozens of registrants who've expressed an interest in this session, and it will include a link to the recording, a copy of the slides, and also information on how you can earn your robotics project certificate, which is offered by Capital. Basically, if you have attended all 4 of these sessions, whether live or virtually or in some combination, then you're eligible for the certificate. I look forward to presenting that to many of you. Now, we do have another series of webinars coming up in addition to the plugged in series. It's called CapTech Talks. And the next one of those is right before Thanksgiving by Dr. Dennis Beatty. And he will be talking about a 360-degree approach to executing vulnerability management program. And then Dr. Bradford Sims, the president of Capital Technology University, on December 4th will talk about a brand new program that we're rolling out called the Online Bachelor of Science Program in Professional Trades Administration. And that's a great program for those who are in the trades and have gone through an apprenticeship. They can leverage their apprenticeship and convert it into college credit to earn their degree. Now, again, use the same URL, captechu.edu/webinar-series to find out more about those or to register. That does conclude my remarks, and we are, it says here, more information about the next webinar, which is on November. We'll go back to that, get that here, on November 6th, okay? All right, are there any final questions? We are doing great on the time, so we have time for any questions that might have come in. All right, Seeing none, I'd like to thank our presenters, and I particularly want to give a shout out to he's had to leave the session already, but to VJ, who has coordinated all of this and brought in all of these experts and mentors to assist in this process. It's been a wonderful opportunity, and I've learned a lot from viewing these. Thank you so much, everyone. And with that, we are officially done, and you may log off at any time. So thank you very much for joining us, and I look forward to catching up with us on November 6th and November 13th. With that, we are done. Goodbye.